at the University of New South Wales. And the first thing I wanted to do was particularly thank Soshan and Sherry from the University of New South Wales and Philippe from Australian National University. And they've been the main organizers for this symposium. And also thanking Susan Warner, who's done a lot of the logistics, and Susan Warner's from Microscope Australia, who are really the hosts of this symposium. So I think we are all excited to hear the talks, and particularly in situ TEM is a growing and becoming a more and more important field. And it's fantastic in terms of how it can study the mechanisms of transformation. So if we can do ex situ studies to see how we start with something and what we end up with. But really the beauty of in situ TEM is we can actually watch and see how things transform. And the other aspect we can think about is looking at directly at how things change with different stimuli. So with in situ TEM, there's a huge variety of different types of in situ TEM. So we can have heating, we can have gas holders and ETEMs, liquid cells, electrochemistry, and even mechanical testing, seeing how things change under stimuli such as light. So a lot of these topics are going to be talked about today, and all the different detectors you can use as well. So we put together a list of very good Australian and international speakers as well, who will touch on this variety of topics. So our first speaker, who I'm really delighted to introduce, is Dmitry Globerg. So he's at Queensland University of Technology. Dmitry spent a lot of his time at the National Institute of Material Science in Tsukuba, Japan, where he really pioneered a lot of these TEM techniques. In Australia, he's been in Australia for about 4 years now, I think, and he's in Australia, he's an Australian Laureate Fellow, which is kind of the highest ranked professor you can get in Australia. And he's been a real leader and pioneer really on the synthesis, but also the structural properties and testing the properties of a huge range of inorganic materials such as nanotubes, nanowires, nanosheets, nanoribbons, nanobelts. So that's what we're going to be hearing about today, and how these things change in the TEM. So Dmitry, over to you.
Thank you so much, Richard. I'm very pleased to be here. So over the next 35 minutes or so, I'm going to introduce to you all type of experiments one can perform inside the electron microscopy column. And consecutively, I go from one method to another method. I spend just maybe 5 to 7 minutes on each technique. Of course, it's much more wider and richer experiments we have done in Japan and now in Australia. But because of time limitations, I will just touch the basis of this research. And I apologize that the logo of my laboratory here resembles coronavirus molecule. It was designed before COVID struck the world. Anyway, with respect to electron microscopy at QET, I'm very pleased first to say that we got very powerful instrument. Just commenced in like July 2021. It's called Geo Near-Arm Microscope. And over next years, I'm going to use this microscope at QET for many in situ experiments. This microscope is very special because it has double correction system for TEM and STEM imaging. And I think there are only a few of such type in Australia now. And it also has some particular features which are not present before. First of all, it has so-called pulsed electron gun. It means that using electrostatic deflector, you can decrease number of electrons and intensity of electrons in a sample, which is very convenient for in situ analysis, especially for beam sensitive materials. This is one feature which is I'm very pleased to have here. Second, the microscope voltage can be tuned from 200 down to 30 kilovolts. It gives again very good possibilities to analyze like biosamples or samples made of polymers. And even at 40 kilovolts, you can see on the left, the graphene lattice is very well resolved. And this is a photo of Japanese engineer, Mr. Sato, who convinced me that, and he showed me the images, that we can get 45 picometer spatial resolution on the images using FFT. So I'm very pleased to have this. And the figures on the right show you it developing over the years. So we just started from digging the big hole. It was in 2019. Then it took a lot of time to prepare a well-assembled room. And finally, we are here. So I'm very glad and very happy to have this instrument in my hands now. Okay, the story on in-situ TEM started from 2006, many years ago, when I was working as a group leader and chief investigator of big international center in Japan at the National Institute for Material Science. Maybe it's one of the best research organizations of the country in Japan. And we started collaboration with Swedish company, so-called Nanofactory. And one by one, I bought 5 different holders from this company over maybe 3 or 4 years. These holders are named here 1, 2, 3, 4, 5. And the one shown here is called Electrical Holder. And then we have a multi-bridge, a lot of like 12 different contacts also for electrical measurements. And if you change gold electrode to AFM cantilever and MEMS center, you have so-called AFM holder. And this one, it's very special. I think it's only one type of such holder in the world now. It has 2 piezo-driven tips, very thin metal tips, which can be soldered inside the microscope using Joule heating or electron beam, and it gives you very rare opportunities to have 3 individual contacts, and you can do like field effect transistors, or you can make thermocouples inside the microscope. I will show you in a minute. And the last buy was in Japan was so-called optical holder. In this case, we have optical fiber protruded through the whole thing from outside of the microscope toward the sample side. And all these holders have something in common. They have piezo-driven, very precise movements of the tip, shown here. The tip can be made usually from tungsten, because tungsten is very convenient to etch, to make it very thin. And these movements are very precise and very delicate. We can master to have this precision better than 1 nanometer during movements. So it means we can touch any sample inside the microscope. A sample usually can sit either on electrode or on a movable tip, depends on the specific setup. So that was story in Japan. And when I came to Australia, I decided that maybe it could be a very good chance to initialize this research as well here. And I was lucky enough to have very talented postdoc in Japan who organized his own company in China. And I think using Nanofactory like ideas and setups, and he designed very like similar holders. Of course, they're different because of patent law, but they like design is very similar. And we bought these holders from his company, and now we have 4 different setups in Australia at QET. Again, we have electrical holder for testing IV curves for samples. We have mechanical AFM holder for testing mechanical parameters like elasticity or plasticity or toughness of the material. We have here optical holder with optical fiber. You can see design is a bit different, but in this case we have optical fiber on the top and movable electrode at the bottom. It means we can do like photocurrent measurements inside the microscope because we have 2 electrical contacts, sample sitting in between, and optical fiber which is able to provide any light onto the sample side of different wavelengths and different frequencies. And the latest buy from this Chinese company, which is called ZEP Tools, was a so-called environmental holder. In this case, we have 2 silicon nitride wafers packed in in the cell with 6 different electrical contacts going inside the cell. And we have a transparent window in between. So it means we can put some liquids or gases inside the cell and seal it by using, for example, epoxy. And then we are able to see through this window what's going on inside the sample, which is not in vacuum, but in real type of environment. And of course, for doing in situ TEM, there are many parameters that which you need to learn and to analyze and to understand how to deal with. First of all, we need to have very sharp probes because we are doing nanomaterial science, so the samples are very small. We need to have probes which are compatible with the size of the sample. So we mastered how to make very thin probes made of tungsten by using electrochemical etching. The tip could be like down to 10, 20, 30, 50 nanometers. So it's good enough for touching the samples. And of course, another parameter, how to drive this piezo material, piezo probe inside. So very high precision in 3 directions. So it also takes some time to master for, especially for beginners, for students and postdocs, how to operate and not to touch, for example, gold base, not to make short cutting and damage the tip and everything, because electronics and mechanics are very delicate for these holders. And for optical studies, it was main task how to protrude the fiber inside the holder, because you know the fibers sometimes are very fragile, and it's about 30 centimeters of length you need to accurately protrude inside the holder. But we mastered and we did it, and now I think we are fully equipped with all these parameters and all these facilities. Okay, first I'm going to show you very original research, because people, I think, they never thought about that this is possible inside TEM. It's called thermal studies. For this, we use our double probe holder. And these probes are made of 2 metals, constant alloys actually, constantan and chromel, and they move independently inside the whole piece of the microscope. And by using very nice manipulations, we can merge this into one very fine thermocouple. I would say it's world's smallest thermocouple, because at the tip it has only like 5-10 nanometers width and dimensions. And then in STEM mode of the microscope, for example, we can drill any type of sample using focus time beam. And then we can put this sample inside the column and attach the thermocouple, which is movable, to some particular point. And we can use focused electron beam of the microscope as a heater So we scan this beam over the sample, and every time we measure the temperature at this point. And as a result, we can get very nicely resolved, specially resolved so-called thermal maps. In this case, we have two types of materials. One is aluminum oxide, which is thermoconducting material, and second is epoxy, which is thermal insulating material. And combination of these materials give you some composite. And by using electromotive force on the thermocouple, which can be transformed to the electrical signal, and by using normalization of the thickness of this sample using, for example, EELS, in situ EELS, we can go to this highly resolved thermal maps, which show you the distribution of temperature and flows of heat inside the sample. Next topic is called nano optoelectronics, and here you can see that we can have light of different wavelengths inside the column, and this microscope, also GO, we used at NIMS, and now we use this microscope as QET. And this optoelectronic and optical research started again like just 5 years ago, and we continue this research actively in here in Australia. And what we can do, we can put any type of material which is actually supposed to be good for solar cell applications, and we can put light on it. At the same time, we can perform deformation inside the microscope by moving the piezo-driven probe. And what's good about this, that we can analyze how material we put inside is good or bad for flexible optoelectronics, because we can analyze specifically signals before, during, and after deformation. And my postdoc here, who used to be also in Japan, Charles Zhang, first author of this paper, succeeded in doing this experiment because it requires a lot of pace and a lot of efforts, but he managed to analyze 138 individual cadmium sulfide nanowires using this very interesting technique. And what we found that independent, of course, every nanowire is different with respect to like optoelectronic signal, but when we analyze statistically all these signals, we found that actually the ratio of dark current and photocurrent is peaked at about in logarithmic scale at only like here. So it means we can surely have material which performs well and almost independent on either the material is bent or not. So it goes for optoelectronic because nobody using one single wire. Usually these wires are used in bunches, in packs. So it means you can be quite sure that your material is very reliable and very systematically produce photocurrent at this ratio. And we can use this optical fiber, which we put inside the microscope, not only as a receiver, not actually as a source of light, but also as a receiver, because we can use electron beam to initiate the luminescence, cathode luminescence in the material, and we can use our optical fiber plus detection system to analyze cathode luminescence signals from the sample. And we did it for this material, again, cadmium sulfide, and we found that dependent on type of defects in the structure, it's very well resolved maps of this material and different wavelengths. You can see that depending on the defect structure, for this material, we may have cadmium vacancies, sulfur vacancies, antisides of both elements, and depending on the particular space location of this defect, the luminescence signal is different. And we again constructed this very nicely resolved maps of this sample. Okay, I switch gears to nanomechanics, what we can do with respect to mechanical properties. And this movie shows you that we can initiate the resonance on the nanotube. This nanotube, actually my favorite material, boron nitride. I studied it back in 1993 in Japan. So we can see that we can use alternating current, which we put on the probe. You can see there's no contact here. We just put the field and the tube starts to resonate. And if you look carefully, we have different nodes of this resonance, depending on the frequency we put on the DC current. And depending on the mode of this resonance, we can nicely analyze elastic properties of these tubes. And also interestingly, because we still have electron beam, we can deliberately create some defects by using electron beam radiation. And we can analyze how these defects affect the elastic modulus, Young modulus of the tubes. This graph is shown here. And also depending on the order of the resonance, the accuracy of these measurements is going up. You can see this is first order, a lot of scattering, second and third order. And we went up to fifth order of resonance for boron nitride nanotubes, and we measure very precisely dependence of elastic modulus on diameter of the tube and also concentration of defects. And we can play with boron nitride tube, just coating it with carbon, for example, because carbon tubes are also very important materials. We have some sandwich made of boron nitride core and carbon shields on these tubes. And depending again on the concentration of and content of carbon and number of shells made of carbon on boron nitride, using this very fine technique, we can analyze how the all mechanical parameters, for example, the kinking positions and way of kinking and charge perturbations at the interfaces are dependent on the number of ratio of carbon layers to boron nitride layers. And it's shown here that finally we can control two parameters. Boron nitride is electrical insulator, carbon is semi-metal. And depending on content of carbon in relation to boron nitride, we can modulate resistivity of the material and we can modulate elastic models of the material. You can see we are in this band, which is very convenient because for metals, carbon nanotubes, boron nitride tubes, silicon nanowires, we have specific range. In this case of B and C nanotubes, we have a very wide range where we can select particular material for particular purposes. And we continued this mechanical work in Australia with my postdoc, Konstantin Farstein, who is here. And we performed the same experiments on aluminum nitride nanotubes. And the essence of this work, because we are armed with electron diffraction inside the microscope, and we can precisely analyze the crystallography. It means that we can grow these nanowires in different directions. For example, one is here, it has a rotation of bezel planes here, and another orientation. And then we can compare elastic properties and mechanical properties, other mechanical properties, as a function of orientation of these single crystals, which is very important. And I think TM is only one way one can do this, to connect particular orientation of single crystals with the mechanical properties on a micro scale. And we also supported this experimental research with theoretical DFT calculations. And the summary of this project is shown here. You can see that depending on the orientation, Young modulus and tensile strength are totally different for this particular material. Recently, we extended this work to new type of inorganic structures, which are called MAXINs, two-dimensional carbides or borides. And again, Konstantin made this very nice work on titanium 3 carbon 2 MAXIN. And we analyze how material performs in tension. You can see direct tensile tests were done here. And of course, in this case, we need to make materials by using FIB. We can analyze crack propagation. We can see how much is tensile strength, Young modulus, all these mechanical parameters. And again, we supported this by molecular dynamics calculations. The next topic is electrochemistry. We can actually mimic the type of battery cell inside the microscope because we have two contacts which can be used as anode and cathode. We can put lithium foil or potassium foil or sodium foil on one part of the system, and we can analyze how material performs under biasing. So it means we can lithiate or sodiate or potassiumate material and see, for example, volume expansion, which is critical parameter for batteries. And this was done by my postdoc here, Joseph Fernando. You can see this is zinc oxide material, which is expanding under the lithiation. And of course, we are equipped with all these TM facilities. We can do electron diffraction, we can do X-ray analysis. We know which phases are formed. We can analyze formation of electrolyte, second electrolyte layers. We can understand whether this material is reversible after lithiation, after first cycle, second cycle, or not. And is it good or not for battery performance with respect to volume expansion. This example shown here, for example, we got completely different volume expansion for zinc oxide particle and the same particles which are also doped with quantum dopes of carbon. In this case, we can suppress the volume expansion dramatically. Next topic is what can one do with respect to nanoelectronics. And for this, I want you to see this very nice experiment which we performed in Japan. And Catherine was my GSPS fellow from Australia, actually. We decided to make some type of core shell structure made of carbon layers. The parameters are shown here, and then put some bias. And in addition, we can make a connection to the core separately and look what was going on here. So we can retract the core of carbon nanotube out of the shell. It's multi-mode carbon nanotube, but we can make it repeatedly. At the same time, we can measure the IV curves of this type of sandwich at every time of this pulling and pushing back. And we found that depending on the length of this core, which we retract from the shell, we can modulate conductance and conductivity. And again, we can analyze helicity of these tubes, we can analyze number of layers, and in the end, this material performs as very nice rheostat. Depending on the length of this core, we have different, depending on this, we call it telescope distance because this material is like a telescope. Depending on this telescope distance, the conductivity is changing. So I would say it could be good for applications in very small devices as a nano-rheostat, we call it nano-rheostat. And another way of using this double probe holder is making transistors. We have three contacts. Two two contacts can be used as source and drain, and one contact can be used as a gate. And we can analyze the electrical behavior of these transistors inside the microscope. You see this setup is shown here. We have very thin carbon nanotubes, only double-walled nanotubes, and by using two parameters, biasing of this tube between source and drain, and electron beam irradiation, we can modulate the helicity in the central part of this tube. And once you know that in case of carbon tubes, the helicity is very much giving rise to different metallicity or semiconductivity of the tube, we can change metal to semiconductor by changing the helicity of this tube inside the microscope in real time, and we can analyze this process by using nanobeam electron diffraction, high-resolution imaging, and we can analyze helicity of both shells. And in case of very thin tubes, triple-walled, double-walled, and you can see that current IV curves are changing as a function of these transformations. As I mentioned, we can change metal to semiconductor and vice versa. This work was published in Auto Microscopy journal, which is, I think, the forefront journal of for any microscopist. And again, we try to understand how this helicity changes are happening inside the tube. We performed molecular dynamic simulations with my colleagues from Moscow University. And again, this is just the gliding of stone walls defects under tension of this tube due to changing in temperature. Anyway, everything was confirmed. And next topic is called nano engineering, because you can play with different structures, with different single crystals, and get very nice imaging conditions for very thin structures. This movie shows you peeling of individual 3 to 4 atomic layers of molybdenum disulfide out of the single crystal. And you can see the precision of this operation is unique. And actually this process mimics the so-called Scotch tape technique used for peeling graphenes out of the graphite single crystals. It shows you what's happening in real time. You can dispatch these layers and put it back. It's very flexible and very sticky procedure. And another interesting phenomenon that when we touch graphene, this is not graphene, it's let's say several layers of graphite, but let's call it multi-layered graphene. When we touch it with tungsten probe and put bias in, you can see very interesting phenomenon, which is also not noticed before. There's very strong interdiffusion process. This tungsten probe eats graphene as Japanese dragon, I would say. And if you check here, this is not tungsten anymore. It comes to tungsten carbide. And if you look carefully, there are new layers of carbon protruding out of this tungsten probe. So actually here we modulate the growth of carbon nanomaterial. We have carbon feedstock, we have catalytic metal here, and we have very high temperature. Because temperature here could be up to 2000 centigrades. We have very high temperature inside the microscope due to Joule heating. So this is very interesting, and the specific conclusion here that tungsten and every transition metal which forms carbides is not good for carbon electronics, because a lot of interdiffusion processes, and one should be very careful because everything will be changing under current flow inside the device. And most recently, my former postdoc, Minsheng Wang, performed very interesting experiments again inside the TM. And we took few layer graphene, and he managed to etch graphene H by using this tungsten probe, which is movable. And here we have type of carbon onion. And this is very interesting process. And we found that we can deliberately select what type of H we want to have ending graphene flake. It could be armchair or zigzag. And it's not only like interesting game and play, but functional properties of these graphene flakes are very much different depending on which H you have, armchair, zigzag, or mixed H at the end of this flake. And for example, this field emission parameters are very changeable depending on which type of atomic structure we have at the end. Okay, that's the end of my talk.
Okay, our second speaker today is John Watt. John is a staff scientist and electron microscopist at the Center for Integrated Nanotechnologies at Los Alamos National Lab. And John has a background in nanoparticle synthesis and high-resolution TM characterization. He joined CINT in 2013 and as a postdoc, and then continued on to be a staff scientist, and has since been characterizing different inorganic nanomaterials, including soft matters, using various TM techniques. So many of these studies involve the use of ETEM and also cryo-TEM under in-situ conditions. So let's welcome John in his talk today on observing inorganic transformation in ETEM. Okay, please, John.
Okay, thank you so much, Soshan, and you can see my slides okay?
Yep, all good.
Okay, well, thank you, Soshan and Richard and the organizers for the invitation. It's my pleasure to present tonight. So I am from the Center for Integrated Nanotechnologies, CINT, which is a joint venture between Sandia National Labs and Los Alamos National Labs. I am based in Albuquerque, New Mexico. Let's get this moving forward. So we have a number of TEMs at CINT. In terms of in situ, kind of the main one that I'll talk about tonight, or today, sorry, it's tonight for me, is our Titan ETEM. So it's image corrected and monochromated. We have Lorentz mode. We just installed 4D STEM, which we're kind of playing around with at the moment. We have a lot of various holders for high temperature, nanomechanics, electrical biasing. I will focus on high temperature and gases tonight, but we do have a lot of expertise with in situ lithiation, electrochemistry, as well as in situ nanomechanics. We have a custom gas delivery cart attached to the Titan. So this was built in-house and gives us very nice control over pressure to the tool, as well as gas mixing. Attached to the ETEM at the moment, we have the K2, the Gatan K2, which gives us high speed and low dose. We also have Protochips Axon, which we just installed, which essentially takes control of the mechanical controls in the beam on the ETEM and keeps your region of interest centered to account for drift. But that doesn't integrate with the K2 yet, so it's a little difficult for low dose things. The other instrument we have at CINT, and I won't begin to act like I know this in and out. This is high energy ion irradiation, so implantation of gases and metals. So the contact for this is Khalid Hattar, and if that piques interest, I can certainly put you in contact with him. We are a user facility, so everything that I talk about today is open to users. And it just takes a short 2-page user proposal. We actually have an open call now that closes September 30th. So any of these instruments are open to users, whether you send samples yourselves, students. There's various ways to access the tools. The other thing we have, which is not in situ, but I will mention, is a newly stood up cryo-EM suite, which is specifically designed for soft matter and beam sensitive materials. So we have a cryo fib, cryo transfer equipment, and a dedicated high contrast cryo TEM. So we have done some work with folks at UNSW around the lift outs of polymers. In terms of today and in situ, I will discuss annealing of platinum islands on branch ruthenium nanostructures. So this is some of the work that I have done with Richard and the team, and then pivot to discussing observing wustite to magnetite nanoparticle oxidation in situ. And so I did have these kinds of things as separate bullet points, but I realized that I'm kind of talking about them as I go. So region of interest, tracking and alignment, and just general things to consider in ETEM. I will try and kind of address these things as I go with the talk. So the first system that I'd like to talk about is branch ruthenium nanostructures. So these were beautifully synthesized by Agus at UNSW. So this is working with Richard. So the first paper, we used the image correction to get very nice surface images of these ruthenium structures, which are highly active and highly stable for the OER. Very nicely controlled surfaces, which are just a dream sample for a microscopist to get sent. The next stage, and I won't talk too much about the chemistry here, I'm just going to talk about the microscopy. So the next step in terms of these structures were growing platinum islands onto the surface of these ruthenium branch structures. And the goal in terms of the collaboration, my part was to observe the platinum annealing on these branch nanostructures from these kind of nodes, nanometer size nodes, anneal into the ruthenium and form kind of single atom active sites. So this was positive ex situ, and then the idea was that we would look in the TEM and see if we could see these things happening in real time. So you'll see here we have kind of a snapshot of this platinum node on zone, nicely crystalline. And then these are the snapshots of the in situ experiment where we heat and introduce hydrogen. And the conditions that I chose for in situ were kind of guided by the ex situ experiments, but of course they don't match exactly. So there's always a little bit of tweaking, which I will kind of go into. But we did observe this annealing away of the platinum nodes into what are ostensibly single atom active sites. So one thing, and Cory will be talking later, who we work with on this. So we were lucky enough to become a beta testing site for the K3 IS. So we do have the K2 on at the moment. We were beta testing the K3 in situ, kind of towards the end of 2019 and into the start of COVID times, which was a real pleasure to have this camera. Very fast video, 150 frames per second at full field of view and up to 3,500 frames per second. So terabytes and terabytes of data. I'm still actually going through the data, a year or two later, because each video takes at least a night to process if you want to, align or extract a region of interest. So it takes time. And we are working with some kind of data analysis, AI, ML folks to try and speed that up. So the nice things about the K3 IS over the K2 is that it's single electron counting in video mode, so you can get very low dose. Probably the nicest thing in terms of a user was that it's easily switchable between modes. So with the K2, you have to switch between static summit mode and in situ mode, take gains, take dark references. With the K3 IS, start the video, take a snapshot, start the video, take a snapshot. So it's really nice. A wide field of view, so about 1.5 times over 1.5 times that of the K2. And as you'll see, that comes in real handy when you're not exactly sure what you're looking for, or you're looking for an ensemble and kind of trying to find a needle in a haystack. So I believe it's about 5.5K by 4.8K. Another thing that was really useful from a user point of view is live frame averaging. So with these really low dose single electron counting modes, to the eye, it's almost imperceptible, any feature, right? Because the contrast is so low, the dose is so low. And what they built in during the beta testing was live frame averaging. So you could average 5 or 10 frames as you went and increase that contrast, increase the signal to noise, which was really nice. and a look back feature. So if you missed your transformation, you know, it was continually grabbing data. So we do have a webinar that my colleague Katie Youngyahan and I did for Gatan, and then there's also a SINT highlight on the Gatan website there. So in terms of the in situ experiment, we have one of the older prototypes heating holders, but it still works perfectly. So initially, to mitigate electron beam interaction or effects, I heated the sample to 500 degrees Celsius, dosed it with quite a high electron dose and saw no change in those platinum nodes. Then flowed 100% H2 gas, so we can go in the ETEM to 100%, up to 10 millibar in the column for our ETEM. If we go any higher than that, then we can void the service contract. And the temperature was ramped to 700 degrees Celsius. So this is one of the things that became evident early in my, figuring out how to run these experiments. Is I always had in my mind that you would be able to switch on and off the gas, right? You could have your sample and you could have this gas front come through, but because of drift, that's just not reasonable. So what you have to do is essentially open up your gas valves, get to a point where you have a steady state with the pressure, and then really your handle to crank is the temperature. If you're seeing transformations happen as you're starting to flow those gases and gradually increase the temperature, you just need to capture them if you can. And you kind of get better and better at knowing the values for the ETEM to get the pressures you want, so you can get there faster, but there will always be some gradient for the gas. And that's just inherent in ETEMs. The look back feature was used here, so 5 seconds. And here, to get contrast, these frames were summed and aligned using a Python code written by kind of a wizard at Gatan, Ben Miller, who I will talk about quite a bit. So you can see here that we have that platinum node anneal into the ruthenium branch structure. The way that this frame is bouncing around is due to aligning common features within the image, and that's been a crucial thing. I'll show a few more examples of that. So this is finding conditions in situ that get the effect that we wanted, and we are capturing that annealing of the platinum. This is just another example and kind of shows you the power of the K3. So if I go back here, you can see this huge wide field of view, right? And then we're just looking down at this select region of interest. So even though we're seeing the business happen right here, we still have all of this data out here that we can investigate. We can use things like AI/ML to pick out features and track features. So here is an example of just another larger region of interest. And you'll see we have multiple platinum nodes anneal into these branch structures. We can also use some code written by Ben to pull out the FFT and create an FFT video. But I think the key thing here is that these cameras have just got so beautiful that rather than zooming in on your one node that you know is on zone and trying to capture that without drift and center it and keep it keep it in the center of the view, you can take this wide field of view and then you can search around within it and find the thing that's doing the business. The other thing is now we can start to get statistically relevant information. So you can look at multiple nodes, match behavior, and you can say that we saw a dozen of these things happening, so we're certain that this is the effect that we're after. And here we just have the structure, which has kind of been aligned and selected down to the region of interest that we really want to see. So I'll start this video. You will see we're nicely on zone, and then you'll see both of these platinum nodes would dissolve into that branch ruthenium structure, and you're left with a very nicely faceted surface, which is what Agus and Richard and the team had predicted ex situ. So it was really nice to get this kind of in situ data matching. You'll also notice here, it may be hard to see, but I'll see if I can pick one up. There's these kind of drifting dead pixels that move around. And so those are static within the image on the camera, but because we're aligning the frames and down selecting regions of interest, we get this kind of drifting pixel. But we end up with this really nice low index surface, and you'll also see the emergence of some moire fringes here as those crystals kind of combine. So I'll shift tack a little bit now and talk about another system that we've been working on, which is magnetite nanoparticles.
I think he's just been disconnected. Oh, hi, John, you're back.
Sorry about that.
Oh, that's all right.
Was it this slide?
Yep.
Yep.
I think you were coming into this one. Yeah.
Okay. Okay. Yeah. So sorry about that. So this is some other work that we've been doing with magnetite nanoparticles. So this is with my colleague at Sandia National Laboratories, Dale Huber. And so magnetite nanoparticles have a lot of different applications. So biomedical, therapeutics, hypothermia, MRI contrast, magnetic particle imaging, and also in soft magnetic components in industry, so inductors and transformers. All of these kind of materials rely on magnetic relaxation, essentially. So you want to have a very good size and shape control because the magnetic relaxation scales R to the volume. So you have a very, very rapid increase in the relaxation time depending on the size. And then you also want to have a very tight size distribution so that you know, especially in something like an inductor, that the whole material is switching at the same frequency. And in things like MRI contrast and magnetic particle imaging, that you have confidence if you have a particle bound compared to a particle unbound. So a tight size distribution is really crucial. You want to have very good crystallinity for the magnetic properties, and you also want to understand interparticle interactions because that can affect the relaxation dynamics. So Dale did a lot of work in developing the chemistry to make these nanoparticles with good size and shape control and a very tight size distribution, so he can control the size within 0.1 of a nanometer. He can systematically increase it. He can systematically reproduce it. And so these are, in my opinion, some of the nicest magnetic nanoparticles around. But it has been shown that, even if a magnetite nanoparticle looks really good on the surface, there can be some stuff hiding underneath that can affect the magnetic properties. So this is a paper from Sarah Majetic and her colleagues using an ion ultrastem, and they showed that they looked at 3 different syntheses, very well-established syntheses for magnetite, and they showed that there was quite a wide variation in the MSAT and the saturation magnetization. And then doing some really nice microscopy, they showed that this was due to the presence of anti-phase boundaries, which has also been seen quite a bit in the thin film literature. So even though we have these, these really nice spherical particles, we also see some variation in MSAT. And what we do is we make, what Dale does, is he makes wüstite first, which is FeO, and that's how he gets the really nice size distribution because there's no magnetic interactions happening in the synthesis. And then they oxidize them in air afterwards, like a post-treatment. And they found that if they do it really fast, they get the introduction of defects, multiple oxidation sites nucleating at the surface. And so you can get a lot of defects happening in rapid oxidation. And then if it's very slow, you get a really nice single crystal of magnetite and your MSAT starts to approach the bulk. So this is another thing that we wanted to watch in situ and see if we could track some of these things happening. So the K3, again, is just beautiful for this. This is another thing of the wide field of view. You see we're at 34 kx and we're getting, good crystallinity of multiple particles over this ensemble. So the first thing that I did was do kind of an in situ. So this is looking at the transformation. So introducing 10 millibar of oxygen onto the wustite and then heating. And here I'm just running it in diffraction mode so I can see where's the transformation, right? Because in situ conditions are not necessarily going to match ex situ. So all I'm doing here is looking for the emergence of magnetite, and then I know where to look for in terms of the in situ experiment. So what we're looking for is the emergence of this peak, the 220 peak around here. And we're looking for this wustite 220 to split into 3 peaks. You'll notice there's a little bit of 220 here, and that's because we have some core shell just from the preparation and the transfer. And you'll see as I heat past it, so this is diffraction, this is an FFT. You can see a really nice splitting of the peaks out here and a really solid immersion of the peak here. So then I can turn to the bright field image on the K3. So I just drop cast single crystal wustite. It does have a little bit of core shell, and that's what this characteristic contrast is here. But again, we're at 56,000, which is a very low mag for getting, nice atomic resolution, but the K3 allows that. Live frame averaging to help with the user visualization and using the look back. And again, we just heat up past 300. And so here, this is kind of another sanity check. This was some code written by Ben Miller from Amatech, and you can find this on the Gatan website in the scripts library. So what this does is it takes the FFT of each individual image and does a radial integration, and then plots that in a 2D map. So what I'm looking for here is the emergence of this 220, but this is not diffraction. This is from the bright field image. But this matched kind of what I saw in the diffraction in situ. And so now I can see that when I'm trying to zero in on a particle, this is kind of the region that I want to look at in terms of being between, frame 1 and the final frame. So this is a video, and this is 10 frames that have been summed and aligned within GMS. So this is taking a region of interest here that look good, and then aligning the frames. So you'll see here, this is an example from literature, which is another kind of sanity check that we're capturing the oxidation. So this was a paper from a few years ago where they showed this characteristic contrast of a core shell particle. And then they showed that if they oxidized from the spinel rock salt core shell through to the pure spinel magnetite, that contrast went away. And so that's kind of what I'm looking for here. You'll see this. This video is a little long, so I'll just kind of skip through. And if you see these particles here, you'll see that contrast also start to kind of bleed out until we have uniform contrast. So this is kind of another a check that we're capturing the transformation we think we are. So then the thing becomes, if we actually want to do some analysis, right, we need to find the particle that's on the right crystal zone to watch that oxidation front, right, to watch that nucleation and watch that front progress, or actually watch the ion come out. And so that's the beautiful thing about the K3 is now, instead of like finding that particle on zone and hoping it stays on zone, hoping it doesn't drift away, hoping you don't get burning of your carbon around it and lose your resolution, you can take this wide field of view, and then afterwards you can go back and you can see, which particle is doing the business, and then you can try and track that one and analyze that one. So this is at T0. You'll see it has that contrast. When I move to the final frame, see that contrast is gone. You'll also see that it has moved. There's always drift. It's just a part of it. And so actually with the K3, even with the field of view, the trick was to find something that was starting down here, at the backside of the vector of the drift, and finishing up here. So capturing the transformation as it went forward. And as I mentioned, there are things now like Axon, which will keep that particle in the center, but they rely on the CETA, so you have to dose your sample quite a bit, which not a lot of materials can handle. So now I'll just go into a little bit of the process between tracking and aligning. So there is always some work to be done on the data, and as I said, these are like terabyte data sets, so it does take quite a little bit to work through them. So the way that I found was successful here was the first step is to sum and align frames, because you need to increase your contrast so that you can identify the particle that you want. Then the next step is to select an ROI and align for drift. So there's my ROI there. So I want to align for drift. And I should also mention that all of this is done in GMS. It's all done in Gatan microscopy software. So, or suite, sorry, Cory. So some of it is with the built-in aligning within GMS, and some of it is with custom code that Ben wrote. So if I just go straight into GMS and try and capture that small ROI, you'll see I have good contrast and I'm aligning for drift.
A minute past now, John.
Okay, and then it's gone. So I missed it. So what I need to do is step down, select the larger ROI. And again, these scripts are available on the Gatan website. And you'll see now there's a little bit of frame integration where this is capturing common features. And then I can step down from that one and I have my single particle. And this is the last slide session. And I have my single particle that I'm losing that contrast. This one's on zone, it's on the zone that we want. And we're seeing that transformation. So now the trick becomes analyzing the crystallography. So as I mentioned at the start, we are a user facility. We do have an open call right now. So we have a fall call and a spring call. Please go to cint.lanol.gov and you can get all the details there. Or you can give me an email at watt@lanol.gov. I'd like to thank Dale Huber, Katie Youngyahan, who is actually moving on to NREL. So please look out for a posting at Sandia National Laboratory in the near future for an in-situ microscopist focusing on electrochemistry, analytics, and nanomechanics. I'd like to thank Barry Carter, the team at Gatan, and of course the team at UNSW. And these are our acknowledgements, and I'd like to thank Richard for putting this acknowledgement in his papers and pushing them firmly over the character limit. And thank you for your attention.
So Ruth is a senior lecturer at the School of Mechanical and Mining Engineering at UQ. So she did her postdoc at DTU, Technical University of Denmark. And I've met different microscopists coming from DTU as well. They're really good at that. And Ruth was then a scientist at Robinson Research Institute in New Zealand before joining UQ in 2016. She has many years, I think more than 15 years of nanomaterial characterization using advanced EM techniques, such as imaging of magnetic vortex pinning in superconducting materials. Her current research interests are in the fuel cell and battery materials, which involve new battery material development and also in-situ characterization of battery or new fuel cell materials as well. And Ruth will be talking about liquid electrochemical TEM today. Please, Ruth.
All right, thank you very much. And thank you very much for the invitation to give this presentation today. So it's really appreciated as well. And I would like to also say thank you to Dmitri. I think it's really nice to have Dmitri so close by, because he also does, well, he's done a huge amount of work in situ. And it's really nice to have someone that's got that wealth of experience that's geographically so close to us. So I will be talking about Operando liquid electrochemical TEM, and I will typically use the word Operando because I just like to distinguish it from in situ where we just have the liquid state, but Operando means that we have the liquid in addition to the electrochemistry, so the bias or the current that we're going to be using. So So I'm Ruth Knibbe, but I am housed in the School of Mechanical and Mining Engineering. But actually a lot of the work that's shown today is done by Dr. Ming Li, and she's a postdoc that's within my group and is also currently based within CMM, the Center of Microscopy and Microanalysis. And most recently, we were lucky to have a new PhD that's joined us, which is Caroline Tao. And so she's also been working on the systems as well and can appreciate some of the difficulties that we have sometimes. And so this is also a collaborative project together with Stan Stogel over in Hitachi in Canada. And then we work together with Human and Eric over in Nakata, also based in Canada as well. So we've been working on this for several years and have learnt a lot in this process. So the thing that's also a little bit different with us is that when we initially went to get the in-situ holder, the liquid electrochemical holder, is that we realized that it was not compatible with the TEMs that we have, so we couldn't buy the off-the-shelf holder, so we had to make our own holder. So that makes it a little bit different. So that's why we have the Hitachi holder, which I believe is the first in-situ holder that in-situ liquid electrochemical holder that's been made, and that's why we also have the collaboration with Nakata as well. So there's a little bit of a different angle. So when you buy a TEM holder, normally they're just limited that you can use it in one particular, or not one particular, but you have a limited number of TEMs that you can use it in. So my group is just a small group. So there's Dr. Ming Li and then Caroline. And we also work a lot with battery systems and development of materials for battery systems. And that's with Lingbing Ran and Emily Cooper. And then also we have some work in machine learning applications as well with Samsia. And we have some unique hardware within our group that's also being developed together with CMM as well. So thank you very much, Roger. And that's also looking at inert transfer from the S to the SEM or to the FIB-SEM, which is really important for our battery materials. And we also have this an Operando holder for liquid electrochemical TM. So we have two holders actually, one for a lower spec instrument and then one for a higher spec instrument as well. And we'll have a look at it. So the thing that is always bad when you follow people that can do all this high resolution work. So I would just show you a high resolution TEM image and say that that's the last time you're going to see this now. We see some lattice fringes at some point, but really once we go into liquid, we lose huge amounts of our resolution. So people get excited by TEM because of high resolution, but we really often don't get high resolution. We don't get these kind of images, but we can actually do this and we can get some nice images in in-situ mode. So what can we do with the Operando liquid electrochemical TEM? We could look at catalysis, we can look at battery materials, electrodeposition, corrosion, nucleation, and also 2D materials. So there's a lot of things that we can do within this liquid system, and that's really useful. And this is just a schematic actually of I'll just switch the pointer into laser. This is a schematic of what our holder looks like that was made by Hitachi as well, and what our chip configuration looks like in our holder. So if we have a look at the Operando electrochemical TEM for battery systems, there's really the two configurations that have been used. It's either the open cell configuration or the closed cell configuration. So if we have a look at the open cell configuration, you can see this on the left. This is really popular and is quite commonly used. And so you typically have a fiber that you can put into an electrolyte, or you make direct contact with a solid electrolyte. And then you can apply a bias, so you can observe what's happening, or you can apply a current and then understand what's happening at that at the interface that you have that's here. So what we do is we work with closed cell systems. So that means we have two chips. We have a base chip and a top chip, and we can sandwich then the liquid in between the two chips. We have then electrodes that are deposited on that base chip. And so from those electrodes, we can observe different phenomena. So mostly we're focusing on dendritic observation, or you can also be looking at things that are of interest would be SEI formation. So these are things that are really unique that we can only look at in the closed cell configuration that you can't look at in the open cell configuration, because they involve the nature of the setup that you have. So really the advantage that we have with the closed cell is that it mimics slightly closer to what we can do with a real system, because we have the real electrolyte in there. So we can use the battery electrolyte that you would use for a typical battery system. We can put that in between our two chips and we can observe the behavior. We also are not limited to point-on-point contact. So that's an important factor, which means that it could change the kinetics that you have of the way that you get the ions then being included into your material might be quite different if you have a point-on-point contact as opposed to your material being completely immersed. But naturally, our shortfall is the fact that we have very considerably low resolution. So with OpenCell, you can get these, high resolution images, and we just can't do that for the closed cell configuration. So I really think that when we design these experiments, we need to be smart about the way that we design it and do a combination of both in situ and ex situ experiments. So if we have a look at the chips that we've got, so this is the Nocata chip that you can see just here, the electron transparent window just in the top section that's there. And here we have a counter electrode, we have our working electrode where we have the active material, and we also have a reference electrode. So another major point I think for the liquid cell is that we have this 3 electrode setup. And so this means that we have the reference electrode that's in there, which means that we can actually very precisely measure the potentials that our electrodes are sitting at. So we can measure the potential of our working electrode. So this means that when we apply a bias, we have a lot better idea of what's been applied to the material that we're interested in, as opposed to when you have a closed cell configuration, you just have 2 electrodes that are attached together. You don't actually know where your voltage drops are occurring when you're measuring the voltage in your system. So this can be it's an advantage that we've got, but naturally we don't have the resolution. But that also means that, we can precisely monitor and control what's happening with our material. We can also then change this configuration to change it to materials that are more suitable for what we actually are interested in. So we could change it to a titanium electrode if that's more suitable for the observation that you need to be making. So if we just have a look at the configuration here, like I mentioned, we have these electrodes, the counter electrode, working electrode, reference electrode, and the electron transparent window here. So our liquid comes in through this hole here, then it circulates around here, past the electron transparent window, and then exits then out the other side here. So what you can see, the image here is actually just a high resolution or just a high magnification SEM image that we have. That's actually, it's a TM image that we have that's taken here just in that electron transparent region. So it's important that you have very, very good quality chips, and problems with your chips can have major impact on the results that you're getting as well. So then we have the bottom chip, we put the top chip on top of there as well. And so we have this then is our top chip here, and you have another window here. And I think just directing some attention towards that window is that what's quite different here is that we have a limited field of view then, because we have a small electron transparent window, we're just putting our electrons through this really small, a relatively small region. So unlike when you put a TEM grid in, or even if we just do straight in situ liquid work, so there's no electrodes, is that you can look at lots of different areas, whereas our field of our region of where we can actually observe is relatively small, and we'll go into also why you want to keep that relatively small as well. Also, the additional complication that you have for that is just the aligning of the chips. So if you have a base chip there, you have a top chip there, if you get the alignment off, then you're not going to see anything. So I think that Ming has developed a very, very high tolerance for these kind of frustrations of getting your chips properly aligned. And so we just have this set up in the holder. So we have bottom chip, top chip, and then the holder lid that's in there with a series of O-rings to make sure that we're not leaking into the TEM, which I'm sure that Roger would not appreciate. So also, because this is a workshop, I just wanted to go through a little bit more of the, some practicalities of what we're doing. So we really need to have the chips. So we start off with the chips. We need to take that into the clean room and work in the clean room. This is also important for us because if we get any kind of dust sitting on that surface, if we put the top chip on top, then we could also have a really, really large gap in between those two chips. And that would really have massive impact on our resolution that we get. So making sure that all the handling is done in a really clean way. So then we can assemble the chips in the TEM holder. And this, as I mentioned, due to the electron transparent windows, is really small. So it's a little bit fiddly just to get that work. A little bit, maybe a lot. It's quite fiddly to get that work. And so that's an important process. So you can do that underneath just a standard stereo microscope to get that alignment correct. So then you can load, so you load the electrolyte into the holder. And so there, we'll see that at another point where we can load that in. And you can see that these 4 holes here is for connecting the potentiostat then up into the holder so that we can do our electrochemistry into the system. So we also need to do a vacuum check before we put our holder into the TEM. So that's just to make sure that we're not leaking. So we've got the liquid, the electrolyte in there, we can put the, and we can just check that we're not going to leak into the TEM. once again to ensure that we're not going to damage the TEM. And then finally, we also need to make electrical connection checks. So this means that we just get a voltmeter, we check with the outputs that we have for the potentiostat and ensure that's actually connected up to the chip, which means that we've got a small wire that connects up to the chip, and then checking that we actually got contact. That's really, it seems trivial, but it's really important to do because if you don't have contact, you're not going to get any electrochemistry to work. So this also is this process takes several hours to get this to come up, to get this up and operational. So, and yeah, it's just a little bit, you need to be patient and very, very calm. So make it even more fun is we can put everything into the glove box. And so we need to make it, if we have air sensitive electrolytes. So the previous one we looked at is the workflow that we have for a non-air sensitive electrolyte. But if we want to make it for air sensitive electrolytes, which most battery materials are, electrolytes are, is that we need to do this in the glove box. And so then anyone that's worked in the glove box will understand that you have limited dexterity and you lose a lot of control when you do things in the glove box. And so now you've got everything into the glove box to do all the alignments and everything that we've discussed before. So that can be an interesting additional step. So I'll just initially talk about some of the in-situ liquid work that we've done on our 120 kV Lab 6 instrument. So this is our holder that's here. We've put it into our 120 kV instrument. We can see that the liquid ports are coming in here, liquid inlet, outlet coming up there. Potentiostat in this instance is connected through to there, and we have a syringe pump there. We can also measure we can measure the pressure that we have within the system, which is important for us to understand. If we have a high pressure, then that could be pushing open the chips, which one could ruin your vacuum in your TEM, but also in addition to that, it could also be pushing open your chips a little bit, which means you're going to destroy your resolution, which is already questionable to start off with. So the other point here I think is important to make is in regards to, and people have already mentioned it, is in regards to the data sizes that we're talking about when we're collecting this data set. So once we're actually, so we can collect our videos, but actually they can get pretty big pretty quickly. And it creates a lot of problems when we're handling the data. So it's not a small series of TEM images that you have anymore, which we used to complain about that they were big. There's some really seriously big videos. So we can also use additional supercomputing processing to actually work with these videos and do manipulation. So because actually the quantification that we get from the videos is really important when we want to make that correlation between what we're seeing in the TEM and what we observe, in the lab, in our battery systems as well. So that we can use a characterization virtual laboratory, and there's a series of ways we can access that, and that's then through a Linux system. But unfortunately, when we work there, we can't work with digital micrograph then as well. So that creates we require then additional tools to be able to do this post-processing analysis. But I can't underemphasize that this is a different workflow that you need to establish, that if you're looking to do in-situ work, is how to handle your data and how to handle massive data sets, and where are you going to store it, and at what point are you going to delete that? Maybe you never delete it. So if we come to the resolution issue that we have with the liquid, so we really just highlight that there's 4 major losses that you're going to have, from chromatic, beam blurring, and signal to noise losses that you have, and you've also got these impact on your transfer function changes. So when you just have the chips together, you just think that you're going to have a chip like this, but actually you just have a bulging chip. So you actually have bulging in between your membranes as you push your liquid through, so it bulges open, which means that in the center here, you actually have considerably worse resolution. So the things that losing our resolution is the nominal space that we have, then the chip bulging, and then also the fact that we have, the silicon nitride membrane that you have in there, and the fact that you're pushing your pressure through, which is bulges out the membrane, and of course your sample. So these are all things that are going to be destroying your resolution. So here, this is us looking at putting the liquid into the TEM. So if we have no liquid in, a partial coverage of the liquid in, complete coverage of the liquid in, so you can basically not see anything, and then you adjust the focus. You can just see and compare the difference that you have between here of an adjusted focus in comparison to no liquid. So there's quite a large difference in regards to your signal resolution that you can get once you just put this liquid in. So that's not even doing anything in the system at the moment. So that's just what we need to be working around. So here, this is the piece of work that we've done, which is looking at zinc dendrite growth. So the zinc dendrites and dendrite growth in batteries are really important. Understand this creates a lot of our, it can cause a lot of our explosions within batteries. And so suppressing dendrite growth and understanding the mechanisms behind dendrite growth are really important in ensuring that we can have safe batteries. So what we have here is we have a zinc sulfate electrolyte. That's here a 0.5 molar solution. And what we have is you have a current that's applied. So we have a 20 nanoamp current, and then we just apply the opposite current. And so what we're measuring is a voltage response and from a potentiostat to see what's happening during this deposition and removal process. So we can see this peak in the voltage that's associated with the deposition, and then an opposite peak when we're actually removing then the zinc, when we're removing the dendrite from there. So we're interested in nucleation processes, growth rate processes from these kind of videos when we're actually doing this. So like I said, we have limited field of view that we have here also because it's in situ and it's relative. We can typically only just be monitoring one spot, and we take a video of one spot and then you can move around to see if it's recreated in another spot. But we're really limited that we have to focus on one spot if we want to be doing post-processing analysis of the system. So that can create some issues there. So here, when we're doing the post-processing as well, we need to be aware of the fact that we have a noisy background. So if you just use standard tools to do this, then you will lose a lot of information because it is actually quite noisy, our background that we have here, because of the fact that we have this liquid layer in there. Finding efficient and ways to get the most out of the way that you can track and trace your dendrite growth. So that takes some work in regards to that post-processing analysis to track where your dendrites are and how they're moving then over time. So this is just some work that Ming then using MATLAB to actually look and understand then that interface with those dendrites that are here. And so on this side here, we can see these really beautiful dendrites that are forming on that surface. And as we zoom in, then we can also get a higher magnification image of that same process there as well. So now we can see something that looks pretty interesting, but we need to move to quantification. So that's when we do the MATLAB post-processing of the videos to understand then the growth rate process at different stage and then correlate together with the voltage that we're applying to understand the nucleation and growth kinetics that we have. So we really have those two main regions. So it's the initial overpotential that we have that's associated with the nucleation, and then you have a longer process that's associated with the growth process that we have here. So we need to track and understand what's happening within that directly with our results that we're getting from the potentiostat then as well. And even actually that process is interesting because we control the potentiostat from one computer and we can control the video from another computer. So they're not actually integrated. So making sure that you actually correlate what's time zero actually is a non-trivial thing. And I'm sure we'll have a better idea. And I'm sure someone has a comment of exactly how they do it and maybe a smart way to do it. But the TEM computer is separate from our other systems. So that can create an issue. And so these are these are the results that we've got from here. So looking at that incubation time that we have for that, and then looking at the growth rate. So we can understand then also, the thing that's also is an important thing to highlight as well is in regards to that liquid flow that you have. If you would run this in a static condition, you would probably hit a diffusion limitation. So you need to have a continuous flow because you need to continuously be supplying ions. If you don't do that and you just hit it in a static cell, then it's going to change the mechanism that you have for your growth mechanism. So understanding what flow rates that you require is important in designing your experiment, because if you run it too low, you're just going to get a mass transport limitation, which could be problematic. So from this analysis, this post-processing analysis, that we can understand the control that we have for the diffusion, which means that we understand how we can design to avoid this kind of diffusion in the zinc ion system. Just, yeah, there we go. So then we move to the different systems. So this is a 200 kV cold FEG system. So now we can start to get something that looks a little bit like lattice fringes, which not as beautiful lattice fringes as other people can show. But, you know, this is pretty exciting when you've been looking at relatively large features in the TEM for such a long time. So this is just some STEM images that are taken here. This is an in-situ image actually, so it's not an in-situ liquid electrochemical system. So we can actually get the lattice fringes in there. So this is, we were quite happy with that. So that meant that the old instrument that we're using, the 120 kV, is that if we can control our processes, we can get a lot better. We can get a lot better resolution. So this is the work that I've got here. And I'll just switch. Not sure how to get it to now run because I'm on the laser pointer. Ah, there we go. It decided to work. So now this is looking at a sodium ion system. So this is an air sensitive electrolyte that we're looking at. So what we're interested when we run these kind of systems is we're interested in looking at the dendrite growth again. So because that's so unique, what we can get in the in-situ liquid system. So we need to understand nucleation and kinetics associated with the sodium ion dendrite growth. But what we're actually observing here is an alloying reaction rather than dendritic growth. So we can see here, this is our electrode surface that's there. And what we can see is a slow progress and evolution of an alloying process. So it wasn't exactly what we're after in that, that's what we wanted to see, but it's important that we can actually track and trace these processes using a higher resolution system as well. So, and so we can see here that we get considerably improved resolution when we run it in the HF 5000. So this is a Hitachi 5200 kV instrument. And so we're running it in an ECPC system with a sodium phosphate electrolyte system. And here we've got a relatively small applied current that we have of just 5 nanoamps for 50 seconds. And then tracking actually what's happening with that alloying system. So from here, we're trying to understand, similar to what it was for the zinc dendrites, is trying to understand the nucleation kinetics that we have, the growth kinetics that we have, and also understanding the impact of the different salts together with the different solvents on the kinetics that we can observe then within the sodium ion system. So this is a different extension for this work. But with that additional workflow that we have working in the glove box, it takes several months to establish a clean and efficient workflow to even get the holder into the TEM to get that to work effectively. So those are the main results. Oh, sorry, those are the main results that I have. So this is an overview for what we've done with our in Operando liquid electrochemical TEM work. So we've really focusing on dendritic growth processes and correlating that together with the results that we get from laboratory-based results. That as far as I understand, we have the first 120 kV system that's done in situ or in Operando TEM for these electrochemical systems. And this is really advantageous for people that don't have super high end TEMs, that this is a low end TEM, and we can still do really nice in situ work with this lower end specification TEM. It's really important to make sure that you get your workflow working perfectly. Anything that's going to push open the distances between your chip will completely destroy the resolution that you have. So making sure that you get your workflow from the start all the way to getting your sample into the TEM is absolutely critical. We've developed a lot of understanding in regards to the losses within the TEM, and this is also important in the way that we design our experiments to make sure that we can get the highest resolution from our system. So we have a very good understanding of how we can manipulate the system to improve the resolution as much as possible. And we now have this experience in regards to observation of the dendritic and alloying processes using in-operando tools. So I think this is the key factors for achieving success in these kind of systems. Thank you, Shoshan, is just to establish very clear research questions, know what your research questions are, know the limitations and what you can do with the system, make sure you have a good workflow, and also when you're doing you need to establish in situ tools for doing post-processing as well. And I believe the best that we can do is when we combine in situ with ex situ tools, and we can get the best out of actually observing kinetic processes, but also getting that high resolution that we can get from in-situ methods as well. And sorry for going over time there, so. But thank you very much. I forgot to say thank you. There's so many people to thank as well. But definitely, Ming, thank you very much for your patience. Caroline, Gila, and Roger, thank you so much for your support. And then everyone at Tashi Nokada, also the Marsden Fund and ARC DP as well. So thank you very much.
Hello, everybody. Welcome back to the second part of our in-situ TM symposium. It's my pleasure to announce our next two speakers. For people that don't know me, I'm Philippe Kremer from the Australian National University. I work at the Center for Advanced Microscopy. So first, I just need to apologize in case I mispronounced your names. My French in particular is not very good. So the next speaker is Marshall Duchamp. He took a position as an assistant professor at NTU in 2016. He has past experiences with microscopy and spectroscopy of electrons in Jülich, DTU, Lausanne, Grenoble, with vast experience in TM and in-situ, working in zinc oxide and other materials. So he has his current interests are in development of TM techniques, in-situ and in Operando TM, with of electrically contacted devices, low temperature experiments, 2D materials with in-situ TM, application of TM to solve material science problems. And this morning he's going to talk about Operando in-situ in a TM imaging in a cryogenic temperature range. Please, Marshall, the floor is yours.
So, as I said, thank you a lot for the nice introduction, and good afternoon still good morning in Australia. It's a bit earlier on in Singapore. So today I will be talking about Operando and in-situ TEM experiments that I have been doing since now more than 4 years that I'm in NTU in Singapore. And as you will see, I will go through different topics to show what we can do and to show you the various experimental capabilities that we have. I won't go deep into detailing for each of these topics as I don't have enough time. So the four topics that I will be presenting today are the following. So first I will talk about high resolution imaging at cryogenic temperature that we can do in NTU. Then I will present mainly the setups that we used to do the in-situ and Operando measurements and the capability of the setup in terms of controlling the temperature continuously, as well as applying electrical stimuli in the same time. And then I will be presenting two examples of materials studied with this system. So the first one will be the ferroelectric Bto material, and the second one will be the YAG ferromagnetic material. So let me start. So first, this is a TM holder that we are using for the work that is being presented today. So it looks like a TM holder, but it has a few different capabilities. So as you can see, so on the left-hand side of the image, you can see that it has some copper beer, and this copper beer can be put into the liquid nitrogen, and that allowed to provide some cold to cool down the tip of the holder. So by immerging the copper beer into the liquid nitrogen, we can cool down the tip of the holder down to 100, 110 kelvins. But what is really special about this holder is the fact that at the end of this holder, we can put a MEMS chip and we can electrically contact the MEMS chips with 6 needles. So usually we use 2 or 4 of the needles to control the temperature, and the remaining 2 or 4 needles to apply some electrical stimuli. On top of being able to apply electrical and control the temperature at the tip of the holder, It is also a double tilt holder, so we can align the object of interest into zone axis to go for high resolution imaging. And the last interesting or special feature of this holder is the fact that it has a heater or active heater in between the rod of the holder and the tip of the holder. So indeed, when the when the holder is immersed into liquid nitrogen, only the tip of the holder it near to liquid nitrogen temperature, while the rod of the holder stay at room temperature. And there is no heat transfer between the rod of the holder and the tip of the holder. That is something really important, because then we don't have any thermal drift due to the thermal expansion of the rod of the holder that may prevent high resolution imaging. And using this holder, so on the right hand side, you can see a typical inner part of the MEMS chip that we use. And the red arrow shows the TEM lamellas that has been deposited on these MEMS chips. I will come back on the procedure how to do that later on. And we can get resolutions down to sub-angstrom resolution. So this is the FFT of gold nanoparticles. So the holder works quite well. It may remind you some similar holder that has been developed like more than 10 years ago now by Ennis group in Delft University. So this is the same technology. What they have been developing this MEMS holder, and they have a spiral which has 4 electrical contacts. They can use the 4 electrical contacts to apply some current through the membrane and to measure the resistance to control the temperature. And they show at the time that they were able to image at high temperature, like 1000 Kelvin, and they were able to follow some in situ transformation at high temperature at high resolution. So what we want to do the same type of experiment, but instead of doing them at high temperature, we want to do them at lower temperature. The first systems that we have studied, it's a lithium nickel manganese oxide, which is used as a cathode material, or LNMO. I believe you all know how liquid ion battery works. So you have an anode and you have a cathode, and during the charge and the discharge of the battery, the lithium is going from the graphite to the cathode, and back from the cathode to the graphite part. And on the bottom side of this graph, you can see the CV curve, which shows the charge and discharge process. What we have added on top of this charge and discharge process is a crystal structure of LNMO when it is in this discharge state and when it is in this charge state. When you are in the discharge state, you can see in the middle that there are 2 columns in this zone axis where we can image, or we can see the lithium atoms. And when the cathode is charged, then these 2 lithium columns are supposed to be empty. And we are supposed to go back and forth from these 2 states when we charge and discharge the structure. But we would like to study this process using TEM and high resolution techniques. So before to start, we look at similar studies that was performed, and one of them was performed on liquid manganese oxide. And they have observed that upon continuous irradiation, so about 1 minute of irradiation under electron beam, the initial spinel structure transformed to the roxal structure. And the roxal structure is easily recognizable because you have an atomic column at the middle of the diamond. So it makes us aware that we have to be really careful of the electron beam induced transformation when imaging such lithium-based material. We did some high-resolution STEM image simulation using Dr. Probe software of the 3 possible phases of this LNMO compound. So on the left-hand side, you have the spinel phase with the 2 lithium column visible, and you have the intermediate phase, and then the roxal phase on the right-hand side, when you have nickel and manganese columns that replace the lithium columns. one more introductory slide. I will go a bit faster indeed. So these are the different degradation mechanism process that we may have when we image such a component. And in 2017, so Lee and co-workers, they presented works and they showed that they were able to image lithium metal at cryogenic temperature, while we know that it's not possible at room temperature. So knowing all of this getting all of this information, we're wondering if we have to go to low temperature to image lithium-based compound inside the TEM. So we expose our specimen at room temperature to a continuous electron irradiation. So you can see on the left-hand side, that's the first image that was taken. Already we have the spinel on the core of the nanoparticle, and we have the intermediate phase on the top of the particle. And when taking the second image, all the structure has been transformed to the intermediate phase. On a different part of the sample, we start with spinel structure, which transform when taking the second image into the intermediate and Roxal phase. So we know that there are some part of the structure that we can see, which is due to the electron beam, and some parts that may be the native structure, but we don't know what is what. So to investigate that further, we look at the change of the oxygen and manganese edge with electron dose. So we can see that at room temperature, the edges are changing quite strongly. But we notice that by following the same edges at cryogenic temperature, the change are much less. And we can see that there is almost no change visible on the oxygen edge. And something else to notice is that the initial edges at room temperature and cryogenic temperature are different, which may indicate that even for real low dose at room temperature, we have already transformed the structure to its non-native state. So knowing that, we went down to cryogenic temperature. This is the bottom row. And we can see that we can increase the electron dose by taking consecutive images and keeps the spinel structure in most of the part of the crystal. We can see that some part of the crystal also are transformed into the Roxal phase, which was not the case at room temperature. So it was one proof that imaging at cryogenic temperature delay, but not completely suppress the phase transformation in this material. And then we went into further to study this material more in detail. So I won't go in detail, I don't have enough time, but then we can follow the EELS edges of the different components present into the material between the core and the shell of the particle, and then deduce some more information on the lithiation and delithiation process. So we'll be publishing that in the near future. Let me go to the second topic, so which is about in-situ and Operando TEM experiment in a continuous and variable cryogenic temperature range. So as mentioned earlier on, I want to present how we can make TEM lamella on the MEMS chips, because when we want to put some electrical contact to the device, we have somehow to transfer the bulk device into the MEMS chips and contact it electrically to be able to apply the electrical stimuli. So I developed the technique to transfer a TEM lamella like 7 years ago now. So what we do, we start with a bulk sample. We extract the TEM lamella as we normally do. You have to rotate the lamella inside the TEM, and then you put the thick lamella onto the MEMS chip with a given angle. And when you have the TEM lamella, which is at 13 degrees from the MEMS chips, then you can further thin it down and make it electron transparent. And by doing this process, so you avoid any raw deposition that you may have when we transfer already thinned down TEM lamella. And at the time also, I was able to find ways to have good electrical contact between the metallic line of the MEMS chips and the polycrystalline silicon solar cells that I was studying at the time. And we can see that the IV characteristic of the TEM lamella were quite similar to the IV characteristic from the bulk solar cell. At least they both have a diode-like IV curve. All right, so now we can start to study material at lower temperature. So just introduction on Bto materials. So ferroelectric materials. So this BTO has 4 different phases at different temperature. So the high temperature phase is the most symmetric phase. It is a cubic phase. And then by going down in temperature, we go from the cubic, tetragonal, orthorhombic at around 5 degrees, and the rhomboedric at minus 90 degrees. Each of these phases has a different polarization direction. And this is explained by the fact that when you are in the cubic phase, you have antiferroelectric polarization in all the in the 3 different directions due to the symmetry of the cubic phase. So you have no net polarization. When you go to the tetragonal symmetry, you break the cubic symmetry. So in the C directions, you end up to have different symmetry as in the other 2. And the symmetry in the C directions give a ferroelectric phase. So you have a net polarization along the C axis. And when you go down in temperature, you have more and more directions that switch to the ferroelectric phase. So in the orthorhombic configuration, you have a polarization along the 011 direction. And in the rhomboedral phase, we have a polarization along the 111 direction. So let's see what we observe when we put this type of sample inside the CEM. So this is a work that was done by my colleague Vaso Tileli back in EPFL, so quite recent work. So what she did, she studies polarization of the ferroelectric phase by applying some voltage at high temperature. So they were able to electrically contact the BTO sample, and they were able to apply some voltage and to follow the motion of the ferroelectric domains upon applied voltage. And they found that when you stay in the range between -1 and 1 volt, you have almost no change in the polarization. So it's what she calls the hard pinning mode. And then when you go to larger voltage, you have a larger displacement of the ferroelectric domain, where the pinning is softer. This experiment was done at room temperature, and then later on she moved to do the same experiment at higher temperature. So by using this similar holder as the ones that I have presented, but instead of going to the cryo range, she went to higher temperature. So she was able to image the tetragonal to cubic transition, and she was also able to image the 2 different domain type in the tetragonal phase. And by using a DPC technique, she was able to get back the polarization at high temperature, so just below the cubic temperature. So it's one of the first, or one of the rare experiments when they are able to combine high temperature and electric field. And now, and then yes, at high temperature, sorry, I didn't mention that, she applies some electric field, and she was able to follow the change of the motion of the ferroelectric domain at high temperature. So now what you can imagine, we want to do the same thing, but we want to do it at cryogenic temperature to follow the transition between the different cryogenic phases. So I won't talk about it. So first, we just follow the change of polarization by decreasing the temperature. So we start from the high temperature cubic phase, 400 Kelvin, and then we went down in temperature. And you can see that the different colors shows the different phase that we have been able to image. Now I will go through the video of the same data set. So we can follow the change. So what we are seeing now, they are banding contours because the experiment were done in TEM mode. And also I want to say that we didn't realign the images due to the stability of the TEM holder. So we can see that now we are in the tetragonal phase with a 90-degree domain polarization, and around 325 Kelvin, we will switch from the 90-degree domain to the 180 domain. So they will appear on the bottom right of the video. We are getting close. You can see the formation of the new phase, and you can see that in a few degrees. So you have this new tetragonal 180-degree domain phase, And now we keep going down in temperature, so until we reach the orthorhombic phases. You can also notice that the band contour are kind of moving a bit, so we have some change in tilt, and we can already see on the top left-hand side a change of the configuration, and this is, we are starting to go in the orthorhombic phase, and now we are fully in the orthorhombic phase. So you can see that the domains are less defined because they are not in a 001 direction, but they are in 110 direction. So we just see a projection of this ferroelectric, of this polarization. And when we keep going down in temperature, so at the time we're able to go down to 200 Kelvin, we're not able to go lower than that. So we didn't manage to reach a lower temperature phase. We just see the nucleation of the new phase, or we almost see it, but it was not low enough. Okay, so by having this huge data set, we can now pick up some frame from the video and analyze the frame. So the first thing that we did, we compare the images that we obtain when cooling and when heating. So you can see on this frame, we have both the orthorhombic and tetragonal phase. This is due to the slightly change in the thickness of the TEM lamella. And we can pick up the same image when we go up in temperature, and we can see that we have two different states, and there is about a 10 Kelvin difference between the cooling and the heating experiment when talking about the transition from the one phase to another one. This is the first observation that we did, and then we can really follow the nucleation and the propagation of one domain. So typically when we are in the orthorhombic phase, so we can see these domains. I already say that they are along the 110 direction. And then we can really pick up one domain and follow the evolution of this domain through the whole temperature range. And what we can see that the orthorhombic domain, they grow along the one, they start from the 10 direction domain of the higher temperature. So what I want to say is that there is a correlation between the orientation and the position of the low temperature domain and high temperature domain. And it can be seen on this video. So at 247 Kelvin, we already have the domain in the orthorhombic phase. And by increasing the temperature, these domains kind of rotate from this 110 direction to the 01 direction. But it stays the same domain. So it's really a domain growth. And we can really pick up this relation between the two temperatures. And yes, I have only 4 minutes left. So now I will switch to the ferromagnetic experiment. So as I said, they are just a preliminary experiment. And now we will combine both biasing and the low temperature for the BTO. So I have my colleague Ruth Knibbe, which is studying the ferroelectric property of YAG, and he can grow YAG on the GGG substrate on differently oriented GGG surface, and he found that the ferromagnetic resonance is different depending on the orientation of the YAG. I won't go in detail, so they asked us to take some nice high resolution images to be able to check the coherency of the interface, and we can see that the 3 samples grown in the 3 different directions are really well epitaxially grown. So this is the 10 sample. So we have the same in the 110, so also perfectly coherent interface, and the third sample, the 111 samples. So this really nice sample can now be used to do our TEM experiment. What do we want to do? So back in 2010, yes, in Tonamura's group, they were able to follow the propagation of the magnetic domain by applying some magnetic field inside the TEM. So they start with no magnetic field applied inside the TEM, and by increasing the magnetic field in one direction, they were able to observe the domain wall propagation and then the transformation to a single domain state. They use Lorentz electronography to measure the fringing field. In our studies, we just use the Lorentz mode of our TEM. So first, we try to do the same experiment. So we start with a device which is a dielectric. Then we have a platinum line and then YAG. I will come back why we have this platinum in a few slides. We take an in-focus image, so we don't see the magnetic domain. And then we go under over focus and we can see the white line or the dark lines, which indicate the position of the domain wall. And then we increase the magnetic field inside the TM, and we can see that at higher field, the domain wall move downwards in that case. All right, so nothing new. So now we can try to do the same experiment, but going to low temperature. So this is what we did. We cool down the sample. Wants to go. Yep. So we start from the low temperature phase. We can clearly see the domain wall boundaries between the two domains. And when we increase the temperature, so we can follow the motion of this domain. And we can see, we can then be in this state where the domain completely disappears. And we can do the same, we can cool down again the sample, and we can see that the domain come back to the same position. And what was quite interesting, like the path from the initial low temperature state to the high temperature state, when we go high in temperature, when we cool it down. And the last thing that we did then, we apply some electrical bias, and by passing some current into the platinum layer, we're able to move the domain wall. And why I want to show that, because it was really the first time that by putting a spin polarized current into the platinum layer, we're able to displace the magnetic domain wall. And now we want to combine this electrical effect with the low temperature. So yeah, sorry for that. So I think now it's time for question.
So next speaker is Cory Czarnik from Gatan. That's why probably all of us already saw his name before in this presentation a few times. So Cory is Gatan Imaging and in-situ product manager. And today he's gonna talk to us about extending EELS analysis for in-situ TEM.
I only want to spend 2 slides on the intro to EELS, right? There's a lot of back talk and discussion about how we get there, and just trying to get to the use case for in-situ integration. So for EELS, here's roughly what happens, right? So you provide a beam, you get backscattered electrons, get Auger, you get CL, lots of sources. But what we're focused on here is how we get the inelastic scattering and disperse it. So the things we can see are valence, sorry, my mouse is bad. There we go. So we can see the difference in band energies, etc. Elemental composition, bonding. So there's a couple approaches we can take. One is we can just treat each experiment as an experiment. So we can just say, you know, at a given temperature, take a pass, take temperature, and we can repeat it. So that's traditionally been the path we've gone down. Moving forward, so, you know, we could do that via brute force. We could just do an experiment. We can do an experiment at, you know, room temperature. We can do an experiment at 100. 200, 300 degrees. But it's hard to coordinate that. You know, I say caffeine dependent. And you have to coordinate drift between the frames. So there are all these caveats, I guess I'd say, that we have to consider. So, but we can still do it. And if we do a single manual sample, we can get HADF images as a function of temperature. And we can still generate RGB maps based on, you know, the data collected at a given temperature. So you can see that there. So we're looking at the copper-2 reduction from copper-2 to copper-1. So you can see that there. Down to the metal, copper. So this is, you can do this manually. Right? There's no crazy thing required to do that. And you can get the seabed patterns as well. So you can see as a function of temperature, you could, you know, manually acquire what you want. So monoclinic room temperature to 350, and then above that, you can see the orientation changes and you get metal. So the question for the manual method is, how can we do this while we make it practical in terms of acquiring data, analyzing data, et cetera, et cetera. So in the first case, we can consider taking a data set and setting a temperature, for example, in this, you know, in situ data set. Set the temperature, read it back, stabilize, done. And then drift correct. And then acquire a new pass. So that's the easiest thing to do, I think. So if we look at how that expands the use case, so you can do it, sure. You can't coordinate multiple data inputs at this point. So data resolution, it's dependent on how much data you collect. So it's very one-off, I'd say. So combining the data sets, we have an option here. Where we can collect a spectrum so you can see in real time the accumulation of signal based on copper 1, 2, metal, and if we play it, you can actually see the generation of the copper metal as a function of temperature. So if you comparing what we started with at nominally room temperature, heated it, we saw a change, we saw another change at 400, at 500, we saw a significant change, I'd say. And then we saw B1, B2, B3, B4. Particles we can analyze based on what we saw. So ultimately, what we want to do is see we want to set temperature, we want to drift correct EELS, EDS, change modes, ideally, and then collect seabed, etc. So this is the Holy Grail, what you can do. So the idea is you can get multi inputs. So you can get HADF, you can get diffraction info, you get EELS, even if it's contaminant, you can rule it out. That's all possible. So
I think there are so many more to discuss behind the scene in Situ TEM. I think Cory pointed out in Situ TEM is really complicated. Not just the external stimuli we have available, all the aspects from preparation, data processing. But it's remarkable to see how vibrant the community is, and also really emphasize how important it is. We're not just using TEM to observe structures, we can now measure properties and understand how things are happening or not happening. And so with this note, I want to close this workshop. And then I would firstly like to thank our national and international speakers. It's really wonderful to have you talking to us, the communities in Australia. And thanks to Dmitry, Ruth, Marshall, John, and then Cory, particularly Cory and John from the West Coast. I know it's very late now in USA. And I really thank you for spending time with us and sharing your valuable experience on in Situ TEM.